Get into thermodynamics. So what we essentially want to learn in this topic is how to measure the heat flow in a reaction. So to start off, let's get into what is thermodynamics. Thermodynamics is the study of energy changes that occur in a chemical reaction. Basically, we're going to be studying how the energy will change as the reaction is occurring. This also includes physical reactions such as changes in state of matter. So what you're going to hear a lot of is the term energy. Okay, so energy is just the capacity to either do work or supply heat. We know energy comes in different forms. What we're really going to focus on energy is in terms of heat. Okay, one thing to know here is a type of energy, the chemical potential energy. This is the energy that is stored in chemical bonds. Okay, so bonds are not like a physical thing in the molecule. These chemical bonds are actually energy. All right, so getting into talking about heat. Heat, which we're going to now note with the letter Q, is the transfer of thermal energy between two bodies of different temperatures. What this means is that heat is nothing but an energy that goes between two things that have different temperatures. What you should know is that heat always goes from warm to cold. So the heat will travel from something that's hot or warm into something that's cold. It radiates outward and it radiates in all directions. So if I have something that's hot, like some kind of like hot piece of rock or something, the heat is going to go out in all directions. Okay, it's not going to be specific to any one thing. Temperature is just the measure of that thermal energy. So we've talked a lot about temperature being a measure of energy. So whenever we talk about temperature now, we're going to discuss that as a measure of the thermal energy. Some other terms that you're going to see come up: system and surrounding. This is just kind of discussing the whole like scenario or what it is that we're actually working with. So the system is just the part of the universe where we're actually like conducting or paying attention to, where we're focusing, while the surrounding is going to be everything else. So for example, if we're talking about heating a cup of water, okay, and okay, so we got our water here. We'll say that the cup of water is the system because that's what we're focusing on, and then everything else will be considered the surrounding. Okay, so everything around the water and the cup of water. Okay, so some other terms that you'll see, not so much right now, but in later parts of this, exothermic and endothermic. So these are different processes in how heat is being transferred or moved. An exothermic process, which we're going to use a negative Q to represent, is when heat is released. Okay, so this is when you feel something that's hot. When you touch something that's hot, it's because of the fact that your hand and whatever it is you're touching are two different temperatures, which means what you're touching has a higher temperature. That heat from it is coming off of that because heat flows from hot to cold and coming onto you. That's why things feel hot. So exothermic processes release heat. Endothermic is the opposite. These are things where heat is absorbed. So now if you touch something and it's cold, it's because your body is hotter than it, so your heat is leaving you and being absorbed by whatever is cold. Okay, so something that's exothermic is going to it's going to lose energy and it's going to feel hot to the touch, while endothermic is going to absorb energy and feel cold to the touch. In terms of chemical bonds, when you break a bond because of energy, you have to absorb energy to break it. While when you make bonds, energy is being released to do so. Okay, we'll get more into exo and endothermic in the later sections. So measuring heat flow, we're going to talk about two common units, the joule and calories. So we'll start off with the more familiar one, the calorie. This one's a little different than what we're used to. So calorie, we're going to kind of really specify here, lowercase c is the quantity of heat required if you want to change the temperature of 1 gram of water by 1 degree centigrade. Okay, so this is just a measure of the energy. If I have 1 gram of water and I want to raise it by 1 degree centigrade, that's what we're going to consider a calorie. Now, the calories we're used to is calorie with a capital C. These, which you can kind of call like nutritional calories. I like to call them food calories since these are the ones that we actually consume. This is known as a kilocalorie or 1,000 normal calories. Okay, so lowercase c is a calorie, while the uppercase C you can call a nutritional or a food calorie. It's 1,000 of the normal one. Secondly, joule, J, probably more familiar with from physics here. This is the SI unit for heat. Okay, so this is the more common unit talking about energy. 1 joule is equivalent to raising 1 gram of water by 0.239 degrees centigrade. Calories. Centigrade. 1 calorie, okay, one lowercase c calorie is equal to 4.184 joules. Okay, so that's got our conversion factor between calorie and joule. So whenever we talk about the heat of something, we usually discuss the heat capacity. This is the amount of heat required in order to raise the temperature of it by 1 degree centigrade. Okay, so when you have a given quantity of something, okay, the more mass it has, the more heat is required. Think about when you're boiling water. If you boil a big pot of water versus a small pot of water, the smaller pot will require less energy to heat and raise the temperature because there's less of quantity of it. Specific heat is the amount of heat to raise 1 gram of something by 1 degree centigrade. Okay, so heat capacity and specific heat may seem similar, but they're actually different. Heat capacity is for any given quantity, whereas specific heat is for 1 gram of it. One thing to note is that the specific heat is very unique to each thing. So every substance will have its own specific heat to it. Okay, these are values that you can just look up in a table. All right, but a specific heat will be different for every substance. So when we're working with heat capacity and calculating that, we have this equation. Q equals to mc delta T. Q is the heat, so that's going to be a measure of energy, so it's going to be joule or centigrade. Remember that a negative Q means heat released, whereas a positive Q means heat absorbed. Okay, and of course heat is energy, so we're going to measure with either joule or centigrade, or calorie, sorry. M is going to be the mass of the substance, which we're going to use in grams. Capital C here is the specific heat capacity. Okay, so again, this is something that you will look up in a table. It's a known value and it's going to be different for each substance. Lastly, delta T, that delta symbol means change. So the change in temperature. The change in temperature is given by the final temperature minus the initial temperature. So with this equation, you can figure out how much heat is either released or absorbed by a substance, depending on how much there is and what the change in the temperature is going to be. So let's do an example here. So the temperature of a 95.4 gram piece of copper has increased from 25 to 48 degrees centigrade when the copper absorbs 849 joules of heat. What is the specific heat capacity of copper? Okay, so we're going to have our equation. The heat is equal to mc delta T. Okay, so Q again is our heat. It's absorbing 849 joules, so we know it's going to be a positive 849 joules. The mass of the copper is 95.4 grams. And we know that the change in temperature, final minus initial, so it started at 25, went up to 48. So it's going to be 48 degrees centigrade minus 25 degrees centigrade, which equals to 23 degrees centigrade. Okay, so if we're going to go ahead and rearrange this, you get that the specific heat capacity is equal to the heat divided by mass times the change in temperature, which equals to 849 over 95.4 times 23. And we get the specific heat is equal to 0.387. Now the unit here is going to be joule over gram centigrade. Okay, so this is something that you can actually just look up. If you were to look up the specific heat of capacity of copper, you would see it's equal to roughly 0.387. Okay, so this equation will be able to tell you how much heat is either absorbed or released what mass is required, what the temperature change is going to be. Basically, it tells you all about the transfer of heat in a substance.